That's a tough act to follow. So let me start with an event that happened several years ago when I had an encounter with the administrator of NASA. I was taking him in to show him the Mars Pathfinder spacecraft. And as we walked across this giant clean room, he stopped me right in the middle of the room, turned to me, looked me right in the eye, and he said, "Brian, I want you to take risk, but do not fail." Right. What should I have said? I didn't know, but I said, "Yes, sir." But what's the answer to that riddle? How do you take risk and not fail? Well, every successful explorer, every successful entrepreneur knows the answer. The answer to taking risk and not failing is being creative in what you do and how you do it. So, why would the administrator of NASA, a notoriously risk-averse organization, feel the need to take risk? Well, I will tell you in a few minutes. Before I go on, though, I need to give you a little disclaimer. Today, I'm speaking not as a representative of NASA or JPL, so all my opinions are my own, and I will be sharing them with you. So, let's go on a little trip. Here's where we're going, the planet Mars. The ancients named it after their god of war, the Roman god of war, Mars. I think they could see a little reddish hue. As you look up in the sky, you notice Mars is just a little bit red. So now, let's fast forward 2 millennia to the late 19th century. The telescope had progressed quite a lot, and from the early simple device of Galileo. And the Italian astronomer Giovanni Schiaparelli pointed his telescope at Mars. And he looked and he saw something really unusual. And he saw some features, and he called them canali. Well, in Italian, that means channel. Well, the American astronomer Percival Lowell heard canali, and he thought canal, because we just finished, the world had just finished the Suez Canal, and canals were on people's mind. So he turned his telescope on Mars, and this is what he saw. He saw these features. He mapped them out. He gave them numbers. He imagined a civilization on Mars. The writer H.G. Wells, who wrote War of the Worlds, did the same thing. He imagined a civilization on a dying world that was more intelligent than Earth. It was looking longingly at this blue planet and thinking, we're going to go there and take over. That was the thinking at the turn of the 20th century, and it continued. Edgar Rice Burroughs wrote The Princess of Mars, beautiful Princess of Mars. Carl Sagan, who became a key scientist in the Mars program, I believe read that book, and that got him interested. He'd like to go meet that Princess of Mars. Of course, in 1938, Orson Welles conducted War of the Worlds on radio, and a lot of people believed it was really going on. And of course, here again, the Martians, they really are always interested in human women, it seems. Especially voluptuous ones. And here, Ray Bradbury, his Mars Chronicles, again showed this amazing world. And so in the 1930s and 40s, before we had ever broken the speed of sound, we were still thinking there was intelligent life on Mars. In 1951, this movie called Flight to Mars, it was subtitled The Most Fantastic Expedition Ever Conceived by Man. And it is still today the most fantastic expedition ever conceived. And I'll talk to you about that in a minute. It's fun to look at they were wearing flight jackets, and of course there's always a beautiful woman around. So, what's the reality? In 1964, after multiple attempts by the Soviet Union and by the US, we sent the first spacecraft to fly by Mars, Mariner 64, 1964. It was able to take only 19 pictures as it flew by. The technology in those days for radio communication, and particularly for image processing, was really primitive. And so what the engineers did, they actually took the raw data, put numbers on it to indicate the intensity of the color, and marked it by hand. They were waiting for the pictures to come down. Here's what they saw. This is not the world of H.G. Wells. This is a pretty desolate-looking planet with craters and other features. But there was still this great interest in Mars. So we continued. Another couple of years later, we sent Mariner 9, and a couple of years after that, Mariner 71. So by the early 1970s, we had an idea of what Mars was. We knew what its gravity was, 3/8 of Earth. We knew it had an atmosphere of mostly carbon dioxide, but a very, very thin atmosphere, but something we were going to have to deal with. And here's what we did. In 1975, we launched the most advanced, sophisticated, and expensive planetary mission that's ever been flown. The Viking 1 and 2 orbiters, and they each carried a lander. The orbiters went into orbit around Mars. We looked down onto the surface. We picked a landing site, and then we let the landers go. The landers propulsively controlled themselves right down to the surface. All 4 of these missions basically were incredibly successful. They landed successfully. The orbiters remained in operation for many years. But the mission, and by the way, that's Carl Sagan standing in front of the lander there. But the mission was to determine whether there was life existed on Mars still, or may have existed. Its job was to scoop some of the regolith from the surface, put it into a set of instruments that would run experiments to determine whether the processes of life or the elements of life or the building blocks of life were present. The answer was no. At that point, interest in Mars kind of disappeared. We went off to study other worlds, Jupiter and Saturn, Venus. But then about a little less than two decades later, the interest in Mars resumed. But it came for a very different reason. Here you see the cost of a set of planetary missions from the first mission Mars mission in 1964 to the very last, our most latest mission, Curiosity, that landed in 2012. The dates, by the way, are all the launch dates, not the landing dates. So you'll notice that there's a big break following the Cassini mission, a mission called Mars Pathfinder. I was the flight system manager and later the project manager of that mission. NASA, something happened in 1991 that changed the future for NASA. The Soviet Union disappeared. All of a sudden, the geopolitics that had driven NASA's funding had gone away. So NASA was looking at a situation where our budgets were going to be going down. We could not afford the kind of missions we had been doing before. So some smart people at NASA said, we're going to do missions in a new program. We call it Discovery. We're going to do missions in 3 years, not 5 years, sometimes 10 years. We're going to do missions for under $150 million in 1992 dollars. And then they came out to JPL and said, and you guys at JPL, we want you to land on Mars. So, hold it now. You want us to land on Mars in 3 years for $150 million? That sounds impossible. Luckily, I work in an organization where if it doesn't sound a little impossible, we're not really interested. So we signed up, and we set out to accomplish this. This was really about a whole new way of doing business. We called it faster, cheaper, better. It was really a cultural change. It was a startup. It was a startup inside a bigger host organization, the rest of JPL, and really attracted some of the most creative people at JPL just because it had this feel of a startup. So we set out to accomplish this mission, and we did. We landed on the 4th of July in 1997. We were on budget. We were on schedule. We had basically done the impossible. We had delivered our lander with the first mobile robot on the surface of another planet. In order to do this, we had to invent or reinvent, from Viking, 25 technologies in just 3 years. That pretty much defines impossible. So there was something else very exciting that happened to us in 1997. We became the internet sensation of that year. Many of you probably don't remember what the internet was like in those days, but it was quite primitive. We ended up having to mirror our servers at JPL in 20 different locations in order to handle what we thought would be some degree of traffic. Well, we had 100 million hits on just the JPL servers alone over the weekend that Pathfinder landed. And the thing I think that really brought the attention was we said we were going to take our data as it came down raw, and we were going to send it out directly out over the internet. This is, social media, the beginning of the idea of that kind of real-time access to information. Of course, when you send stuff out on the internet, you got to be careful about what you get back. And there were people that sent us things that said, and they actually tried to communicate this, NASA is hiding this. This is what's really going on Mars. Well, that's not quite true, but we had a lot of fun doing that. While Pathfinder was under development, we were already looking forward to the next mission, because missions to Mars happen every 26 months. That's when the geometry of Earth and Mars line properly. Gives us the minimum energy to get to Mars. So we were already looking at the next generation, and we were pushing this idea of faster, better, cheaper, even harder. We were going to do not only a single lander, we were going to do an orbiter too. And so we were pursuing that approach, even before Pathfinder had landed. But the thing that Pathfinder did that showed something really extraordinary was illustrated here in this cover of Time magazine. This is what I believe was not a recognition of NASA or American skill, but of human accomplishment. The human people really connected with this. This picture was on the front page of pretty much every magazine and newspaper in the world at that time. Humans were proud of what we'd accomplished with this mission in space. So now let's fast forward a couple of years to 1999. And one of these this mission followed Pathfinder. The Mars Climate Orbiter was on its way into the atmosphere, on its way to Mars. It failed to get into orbit. In fact, it actually burned up in the atmosphere of Mars. What was the cause? Well, the media reported that it was a failure to translate an English unit to a metric unit. We do all our analysis, all our flights in metric units. It doesn't get any more embarrassing than that for a rocket scientist to get a unit conversion error wrong. But I'm going to tell you what I think the real root cause is in a few slides. Well, that was bad, but we were sure hoping this lander would make it. Here's the Mars Polar Lander, a propulsive lander, not the airbags of Pathfinder. This failed as well. The root cause? Probably a software error, a very simple one that nobody in this room would make today. But we should have caught it in test, but we didn't. So we lost this lander. 2 strikes. I'm in a 1 strike and you're out business. The risk perspective that we had started with in faster, better, cheaper, all of a sudden hit the brakes. We were very risk on with Pathfinder. After this, it was risk avoidance. We did get another orbiter, Odyssey in 2001. That worked extremely well. And we would basically use that same lander design again in 2008 for the Phoenix landers. But again, we didn't want to lose the Mars program because of these failures. So a few smart guys at JPL said, what if we go back to Pathfinder? Let's go take the Pathfinder technology and apply it. And that's what we did. We said, let's now, instead of a lander and a little robot, a mobile robot, let's make a bigger robot and let's give it mobility to go much greater distances. And that's what we did. We created Spirit and Opportunity to fit inside the Pathfinder lander. And we built 2 of them. Again, in this risk-off environment, we felt, let's build 2 in case we lost 1. Both of them landed successfully. The airbags worked perfectly. The rovers were designed to operate for only 3 months. They both operated for over 10 years, and Opportunity is still roving the surface of Mars. Again, we were looking ahead. What's the next generation of rover? We said, we've been doing mobile geologists. Let's see, what else should we be doing? Well, how about a mobile chemist? How about a mobile biochemist? And so we picked a new payload, a much bigger payload. We wanted to be ability to actually get samples below the surface. And we wanted to be able to go anywhere on Mars. So we actually used a radioisotope power system. This became a very big rover. And we realized we were going to have some interesting challenges getting this down to the surface. You'll hear about that in a minute. Here's Curiosity. She's doing a selfie. She's got her arm out with her camera looking back at her. Spectacularly successful mission, now operating originally for 2 Earth years, 1 Mars year. She's approaching her 4th Earth year anniversary. And of course, we love when the social media connects what we're doing with what's popular around the world. So I heard a little talk yesterday about artificial reality. Well, we've been doing some work with Microsoft on augmented reality. And it doesn't make you sick like maybe other approaches do. But what we've done is taken this really, really rich data set of our images from Mars, and then we give the engineers and the scientists the headset, and then I've actually walked on the surface of Mars. I've looked underneath the rocks. I've looked at places where I said, that's a good place to go drill. And that's what we're doing. We're taking this new technology and applying it to how we design and operate our missions on the surface. So here we have a family photo, 3 generations of innovation, from Sojourner, just 12 kilograms, to Spirit and Opportunity, 180 kilograms, to Curiosity at 950 kilograms. Mars is hard. At the time we were ready to launch Pathfinder in '96, there had been 30 attempts to either fly to Mars, orbit, flyby, or land. Only 10 had been successful. We'd made it to the launch pad against the odds, but here, maybe not. Maybe the odds were still against us. As of today, we've had 21 successful missions, but we've had some failures still. Mars is particularly difficult. And why is that? It's this graphic. This graphic illustrates the process that we have to go through as we fly in from deep space at high velocity to bleed off all that energy, to go through a number of steps. Actually, more than 70 specific events have to happen just the way we design them, just when we design them, in order to get down to the surface. The design of this process is a combination of tests and computer simulations. The only place you can test this system end-to-end is at Mars. And this process is controlled by just one computer on board the lander. It's completely autonomous. It takes 7 minutes. All we can do is watch it, because there's a 14-minute time delay. It's a very surreal experience, knowing something's already happened while you're looking at the data. But this became, to us, what we called the 7 minutes of terror. So now I'd like to introduce you to some friends who will explain to you how we came up with a very novel way to deliver this 950-kilogram rover to the surface of Mars. Roll tape, please.
when people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
That's rocket science. We actually made this video, a great young filmmaker made this video, and he made it without permission. He just went out and he had this idea, and he got people together, and he put this together. And it's really tells this story so beautifully. I work at the Jet Propulsion Laboratory, JPL. Some people think that stands for just plain lucky. Well, there was no luck in this. We were counting on really good engineering. So let's talk about that for a second. I'd like to introduce you to a special group of ladies, part of the team that built the Mars Pathfinder lander and Spirit and Opportunity. And they build the cabling, the wiring that interconnects all of our electronics. They're just one of the many teams it takes to build a spacecraft. What do I look for in a team? I look for talent, obviously, but I look for ownership. I look for people who have a personal commitment to doing their job well. And then I also look for ownership amongst the team for a commitment to the total mission. And then there's trust. The team members need to trust each other. They need to trust me. They need to trust that they can bring me bad news. And then I need to trust them. If there's somebody on my team I didn't trust, they didn't last very long. Andrea mentioned earlier today about what you need for creativity in a team. And diversity is absolutely essential. Diversity in the skills, the experience, and in their network, who they're connected to, who they know, who they can go to get answers to questions, to get information. When I'm building a team, I want people like Tom Revellini. You know, you saw Tom in the video. Tom was the guy who was responsible for building the airbags. We started out using the most powerful computer on Earth at that time, Cray XMP, and we could run it for hundreds of hours and get only seconds of simulation of how this thing would behave. So we ended up going back to an old-fashioned way of doing engineering. Build it, test it, break it, fix it, and do it again. And that's what Tom's team did. But what made Tom successful wasn't his IQ, it was his EQ. It was his drive, his judgment, his resilience, his ability to pick himself and his team up after a failure, and there were a lot of them, and get back in the game. Today, I can find a lot of smart people out there, but I look for that EQ. I look for people with drive, with energy, who are fired up when they tell me what they've done and what they want to go do. Those are the people I hire on my project. Communication. These are some antennas we have. We have a sets of antennas around the world in Madrid, Canberra, California. We can keep on track of our spacecraft 24/7. The key to communication, though, is understanding, mutual understanding. Now, that Mars climate orbiter I mentioned, the unit conversion error, in my view, that was not the root cause. The root cause was a communication breakdown. The navigator could see the spacecraft was not following the trajectory that he thought it needed to follow, but he was not able to convince his management and the engineering staff around him that he really had a real problem. If he had been able to communicate effectively, we could have easily changed that orbit, and that spacecraft would be in orbit around Mars today. So I really try to look for ways to make sure communication is clear and effective. Technology. I mentioned 25 technologies on Pathfinder. This is one of the key ones. This was the first modern computer to fly in deep space. It was only a 20 million instruction per second computer. And my God, I had 4 mega memory. Can you imagine? But this was one of those technologies I really needed, but it was there to mitigate a risk that I really didn't understand, and that was the software. I mean, I love my software team, but I don't trust them any further than I can throw them when it comes to estimating the scope of a job. We figured 30,000 lines of code. We needed 150,000. We were able to do that because we had a modern computer. We could program in a modern language, C, and we had all the tools that you need. So I took a risk in hardware to mitigate a risk in software, and that paid off really handsomely. Our motto became test, test, test. Pathfinder, Spirit, Opportunity, and a number of other missions we fly are what we call single string. There's no redundancy. One failure in the software, one failure in the hardware that you don't catch could cost you the mission. So we test the hell out of everything. And here you see us testing in Earth orbit, or sorry, in Earth atmosphere, our parachutes. And here you see us testing in a large chamber, the Curiosity parachute. I know I've heard the name Elon Musk a lot. I've met Elon. He's quite a character. SpaceX has set out to do something that nobody has ever tried to do, which is to land the first stage of their rocket back on Earth, because they could reuse it. They've been successful multiple times. Now, recently, they've been very, very successful. But they've also had failures. But their culture is about testing. Every engine they fly, and it takes 9 of them to launch a Falcon 9, has got a full lifetime of test on it before it even gets to the launch pad. That's really unprecedented. But testing is really critical to our success. Here this is another team. This is the team that was responsible for the building and the testing of Pathfinder, and they went on to work on Spirit and Opportunity. I learned something over the course of Pathfinder. I wrote in my book, High Velocity Leadership. The role of leadership. It's glue and grease. Glue is what holds a team together, keeps them on focus, on target. But grease, I think, is even more important. It's what the leadership does to facilitate getting the work done, to cut through the red tape, to enable the environment that your team can be successful in. Glue and grease. So, here's where we've been on Mars. The InSight mission is one that'll come in a couple of years now. Also the European ExoMars will be coming in a couple of years. So, what have we learned? In my dreams, I see Marvin the Martian on Mars. Because the reason we have been pursuing this exploration of Mars is to try to answer that question of, are we alone? And Mars represents an extraordinary laboratory to try to figure that out. So the first thing that you notice that anywhere on Earth you find liquid water, you find life. So we've been looking for water. We've been following the water. And we have evidence clearly from Pathfinder and Spirit and Opportunity of sedimentary rock, which only forms in the presence of water. These hematite blueberries also only form in the presence of water. We know there's been water on Mars. We see all the features, but we don't know when, and we don't know for how long. Here we actually see active water processes. This is images from the Mars Global Surveyor. Actual streaks of water coming down a crater on Mars. So there's the basic water is there somewhere. This is one of my favorite pictures from the European Mars Express. This is Valles Marineris. This is a place that I would love to go explore someday when we've really got the tools to do it. It'd be a great place to send astronauts. And here's what we've learned from Curiosity. Curiosity, we landed in a crater in which we were very sure we were, and now we are certain, had water. Gale Crater. So we see the evidence of sedimentary rock formations, but now with Curiosity, we can actually drill below the surface. We can actually get material to bring and put into our instruments that can tell us the chemistry, the mineralogy, and if there were clear evidence of something biologic, maybe we would see that as well. We haven't seen that yet, but we've seen all the building blocks of life are there in Gale Crater. So let's look into the future. So you see a trail of orbiters and a trail of landers. We've been following the water. We've been exploring habitability. Habitability in the past, future habitability, ability for humans to live there. We're looking for the real signs of life. Did life ever show up on Mars? And what that's going to mean is we're going to need missions that can actually bring back samples. We probably can't be definitive until we've brought something back from Mars. And we've been working on the idea of a Mars sample return for almost as long as I've been at JPL. But this decade, maybe the 2020s, we'll have a chance, because the next rover we send to Mars will actually be caching samples that would actually be able to be brought back, put into Earth-based laboratories, and maybe we'll find the evidence that we're looking for. And the rovers, of course, have a lot of places they hopefully can go. So now I want to shift gears a little bit from robotic exploration to human exploration. I had the opportunity to work in the human exploration program in Johnson Space Center for 3 years. So I've got a really strong connection with my friends in the human space program. I'm sure everybody in this room has seen Martian. If you haven't seen The Martian, please do. From my point of view, it's a wonderful film. Ridley Scott did a great job of keeping the science and engineering as accurate as Andy Weir's book did. Andy did a pretty good job. But keeping humans alive on Mars or in space is very hard. When Mark Watney, my favorite scene in the movie is Mark Watney is sitting there thinking about what the situation he's in, and he says, "I'm going to science the shit out of this." Well, what he really meant to say was, "I'm going to system engineer the shit out of this." Because that's what he did. He said, "My level 1 requirement is to keep myself alive until I can be rescued." And then he went off to solve all the other problems that he needed to solve. He found potatoes. He needed water. So he went and took rocket fuel and actually burned it up, which produces water. It's a pretty risky thing to do, but he solved it. He needed to communicate back to Earth. And he went and found the Mars Pathfinder lander. I like that part in particular. And brought it back and was able to communicate back to Earth to let him know he was there. And they could mount the rescue. That was so impressive. So here's a little more realistic view of the human program. We've been in low Earth orbit since 1972, the last Apollo mission. We've done some amazing things. The space shuttle, a true wonder of the modern world in my view. The space shuttle, which enabled that. But we've got to get beyond low Earth orbit. So the next place we're going to go back to cislunar space, to the space between Earth and the Moon and around the Moon. And we're going to start building up capabilities there and send humans there, because we can test things a little more rigorously there without the easy fallback to going back to the surface of Earth if we're in low Earth orbit. And from there, then we'll actually venture out for longer sorties with humans, developing the capability to keep humans alive, not from days, but months and even years in space. That is a real hard problem. Here's a key building block, the Space Launch System. This is a Saturn V class vehicle. It can deliver 130 tons to low Earth orbit, and it can deliver humans to the moon. Here's the vehicle that can do that can carry humans to the moon. It's the Orion spacecraft, designed to carry 6 people. Probably the first missions will only be 2. And it uses a European-built service module. This is the mission I'm currently the project manager of. It's called the Asteroid Redirect Robotic Mission. It's a critical part in this path to humans in deep space. What we're about is using advanced electric propulsion technology to rendezvous with an asteroid, a 300-meter class asteroid. Map it, find a 3-meter boulder, land right on that boulder, pick it up, take it off the surface. Once we've done that, we're going to demonstrate the ability to actually change the trajectory of that mother asteroid by a tiny amount, just enough to measure it, over 30 days. And if that wasn't enough, we're now going to bring that 20 tons worth of asteroid material back to cislunar space, put it in orbit around the moon, and send humans out to explore it. That sound a little impossible? We love it. So this is a key building block in our thinking toward the future, including even this idea of using electric propulsion along with chemical to deliver a habitat with crew into the Mars system. Coming back to my friends at SpaceX, Elon has said he really created SpaceX because he wanted to go to Mars. And this is the Red Dragon. This is a capsule, which is the same derivative of the version that are flying to space station now. But we at JPL and NASA are working with SpaceX to help them solve some of the problems that they're going to need if they're going to be able to land on Mars. They're not delivering crew at this point. There's no way to get crew back off the surface of Mars. But again, commercial company, is really pushing very hard to do this, and they can take risks that we on the government side can't. So we were wishing Elon and the SpaceX team a lot of luck. But here's where we're going. This is a drawing of a sustainable, self-sustaining Mars base where there would be food and water and a crew who would be able to live there, maybe for a very long period of time, and continue the exploration of Mars. Because one of the things about humans can do things much more efficiently than robots. And it turns out in this environment, that could be the argument for sending humans to Mars. So I'd like to leave you with this image. This is the picture taken from the surface of Mars, looking back at Earth. You are here. And I envision, I dream maybe about the future in which humans are on Mars. And I think of an astronaut family, a mother and a father, and one of their kids, them looking up at the sky and pointing up and saying, that's where we came from. Thank you very much.